Welcome to Sleepy Science, where we explore the fascinating mysteries of our universe with a voice as soft as moonlight and facts as comforting as a warm blanket. Tonight, we're going to drift through one of the most misunderstood phenomena in all of nature. We're going to discover radiation, not as something to fear, but as an ancient, ever-present companion that has shaped every moment of existence since the beginning of time. So settle in, adjust your pillow, let your breathing slow, and prepare to discover that the universe around you is quietly glowing, humming with an invisible energy that connects every star to every atom, including the ones that make up you. Our story begins not with danger or disaster, but with something far more peaceful. It begins with light. Every morning when you wake, sunlight streams through your window. That light, that warm golden glow that paints your room, is radiation. The gentle warmth you feel on your skin, that's radiation too. It's electromagnetic radiation, traveling across 93 million miles of empty space to reach you, arriving in a continuous wave of energy that has journeyed for about 8 minutes and 20 seconds from the surface of our star. But here's what makes this beautiful. Radiation isn't some modern invention or artificial creation. It's one of the fundamental ways that energy moves through the universe. It's been here since the very beginning, since the first light blazed into existence 13.8 billion years ago. Let's think about that number for a moment. 13.8 billion years. That's how long radiation has been traveling through space, carrying energy, creating light, making warmth, shaping galaxies, and eventually making life possible. Right now, as you lie there listening to these words, you're being gently bathed in radiation from countless sources. The device you're using to listen produces a tiny amount of electromagnetic radiation. The walls around you contain trace amounts of radioactive elements, like potassium-40, which emit gentle particles. Cosmic rays from distant exploded stars are quietly passing through your body, thousands of them every minute, like invisible threads connecting you to the far reaches of the universe. And yet, you're perfectly safe. You're fine. You've always been fine. Because here's a truth we need to understand from the very beginning. Radiation isn't a monster lurking in the shadows. It's simply energy in motion. It's photons dancing through space. It's particles spinning away from unstable atoms. It's the universe's way of seeking balance, of distributing energy, of transforming and creating and sustaining. Let me tell you about the word itself, because words have their own gentle stories. Radiation comes from the Latin word radiare, which means to shine or to emit rays. In 1760, when the word first appeared in English in its modern scientific sense, it simply meant the emission of energy. Not danger, not destruction, just emission. Just the act of sending something outward, like light spreading from a candle flame. The ancient philosophers, though they didn't have our modern understanding, sensed something true about light and heat. The Greek philosopher Empedocles, living around 490 before the Common Era, proposed that light was something that traveled, that moved through space. He imagined fire streaming from the eyes. He was wrong about the mechanism, but right about the essential truth. Energy travels. Centuries later, in the year 1604, Johannes Kepler studied the way light diminishes with distance and formulated ideas about radiation that would later help explain how energy spreads through space. His work was mathematical, precise, and utterly peaceful in its implications. Energy simply follows rules. It behaves according to principles. It spreads in predictable, understandable ways. Now let's drift back even further. to the very atoms that make up everything around you. An atom, as you might remember from school, is mostly empty space. If you could expand an atom to the size of a football stadium, the nucleus would be smaller than a marble sitting at the center of the field. The electrons would be tiny specks, orbiting somewhere up in the highest seats. Everything in between, empty, void, nothingness. And yet, this mostly empty structure is held together by forces so powerful, they define the nature of matter itself. The nucleus, that tiny marble at the center, contains protons and neutrons. Protons carry positive charge. Neutrons carry no charge at all. And these particles are squeezed together in a space so small it defies ordinary understanding. Here's where it gets interesting. In a gentle, almost meditative way, the protons in a nucleus should repel each other. They're all positively charged, and like charges, repel. It's one of the fundamental rules of electricity. Put two positive charges near each other, and they push apart. And yet, somehow, inside every nucleus, these protons stay together, dozens of them sometimes, all crammed into a space billions of times smaller than the width of a human hair. What holds them together is called the strong nuclear force, and it's one of the four fundamental forces in nature. It's incredibly powerful, but only at incredibly short distances. Get protons close enough together, and the strong force overwhelms their electromagnetic repulsion, binding them into a stable configuration. But here's the thing. Not all configurations are stable. Some combinations of protons and neutrons fit together perfectly, like pieces of a puzzle that have found their proper places. These nuclei can sit unchanged for billions or even trillions of years. They're happy, if we can use such a word. They're balanced. They're at peace. Other combinations don't quite fit. They're slightly wrong, slightly unbalanced, like a Jenga tower that's been built just a bit too tall. These nuclei are unstable. They're radioactive. And when a radioactive nucleus finally releases its excess energy, when it finally lets go of that instability and transforms into something more stable, we call that radioactive decay. It's not an explosion. It's not violence. It's simply a transformation, an atom releasing energy and becoming something new, something more balanced, something more at peace. The discovery of this phenomenon is itself a calming story, because it reminds us that even the most profound truths often arrive quietly, in moments of careful observation and patience. In 1896, a French physicist named Henri Becquerel was studying phosphorescence, the gentle glow that some materials emit after being exposed to light. He had wrapped some photographic plates in thick black paper to protect them from light, and he placed some uranium salts on top of the wrapped plates, planning to expose them to sunlight and see what happened. But the weather in Paris turned cloudy. Day after day, clouds covered the sky. Becquerel, waiting for sunshine, simply left his experimental setup in a drawer. When the sun finally emerged and he developed the plates, expecting to see nothing, he found something remarkable. The plates had been exposed. The uranium salts had created an image right through the black paper, even though they'd been sitting in a dark drawer the whole time. The uranium, he realized, was emitting something on its own, not because it had been energized by sunlight, but simply because that's what uranium does. It radiates. It shines with an invisible light, not from any external source, but from within its own atomic structure. Becquerel had discovered natural radioactivity. Soon after, Marie and Pierre Curie, working in a converted shed in Paris, began to study this strange phenomenon more carefully. They processed tons of uranium ore, boiling it, dissolving it, crystallizing it, over and over, in search of the substances that were most intensely radioactive. Working in conditions that would seem harsh today, but which they approached with methodical calm. They isolated 2 new elements. They named one polonium, after Marie's homeland of Poland. They named the other radium, from the Latin word for ray. Radium glowed. Actually, visibly glowed. If you took a sample of radium salt into a dark room, you could see it emitting a faint, ethereal light. It was a blue-green glow, gentle and strange, like moonlight crystallized into matter. The Curies would sometimes visit their laboratory at night, just to see their radium samples glowing in the darkness. Marie later wrote about these visits with a sense of wonder and beauty, describing the faint light as one of the loveliest sights she'd ever seen. They didn't yet know about the dangers. They didn't yet understand the full implications of what they'd discovered. But they had opened a door into the atomic world, and what they found there was not chaos or destruction, but transformation. Elements changing into other elements, energy flowing according to invisible rules. Nature revealing one of its deepest processes. Let's pause here and think about what we've learned so far. Radiation is simply energy moving through space or particles being emitted from unstable atoms. It's been part of the universe since the beginning. It's in sunlight. It's in the rocks beneath your feet. It's in the very atoms that make up your body. The discovery of radioactivity wasn't an invention, but an observation. Humans didn't create radiation. We simply noticed it, measured it, and began to understand it. And now, let's go deeper. Let's talk about the different types of radiation, because not all radiation is the same, and understanding the differences will help you see why some forms pass through you harmlessly by the billions, while others require our careful attention. When scientists first began studying radioactive materials in detail, they noticed that the emissions seemed to behave differently. Some were easily stopped by paper. Others could penetrate paper but were stopped by thin metal. Still others could pass through substantial barriers. A physicist named Ernest Rutherford, working in the early 1900s, performed elegant experiments to understand these differences. He placed radioactive materials near magnetic fields and observed how the emissions curved. Some curved one direction, some curved the opposite direction, some didn't curve at all. From these observations, he identified 3 distinct types of emissions, which he simply named using the first 3 letters of the Greek alphabet: alpha, beta, and gamma. Alpha radiation, he discovered, consisted of relatively heavy particles that carried a positive charge. Later work showed that alpha particles are actually just helium nuclei, 2 protons and 2 neutrons bound together. When an unstable nucleus emits an alpha particle, it's essentially spitting out a tiny helium atom without any electrons. Alpha particles are, in the grand scheme of radiation, gentle giants. They're relatively massive compared to other types of radiation, and they're easily stopped. A sheet of paper stops them completely. A few inches of air stops them. The dead outer layer of your skin, those cells that are already being shed and replaced, stops them entirely. If you held a small sample of alpha-emitting material in your hand, the alpha particles would be completely absorbed by your skin before they could reach any living tissue. They can't penetrate. They can't go deep. They're too big, too charged, too easily absorbed by matter. The only danger from alpha emitters comes if you breathe them in or swallow them, getting them inside your body, where they can irradiate sensitive tissues directly. But from outside, they're harmless. Beta radiation consists of much smaller particles, electrons, or sometimes their antimatter counterparts, positrons. These are emitted when a neutron in an unstable nucleus transforms into a proton, or vice versa. The particle that's released carries away the excess energy. Beta particles can penetrate paper, but they're stopped by a thin sheet of aluminum or even thick plastic. They can travel a bit farther in air than alpha particles, maybe a few feet, but they too are relatively easy to shield against. If beta particles hit your skin, they might penetrate the dead outer layer and reach living cells, potentially causing damage. But we're talking about low energies here, mild effects, easily managed with simple precautions. Gamma radiation is different. Gamma rays aren't particles at all. They're photons, packets of electromagnetic energy, just like visible light, but with much, much higher energy. They're emitted when a nucleus releases energy without changing its number of protons or neutrons, simply dropping to a lower energy state. Gamma rays can penetrate deeply. They pass through paper, through plastic, through metal, through your body. To shield against gamma rays, you need dense materials and thickness. Lead works well because it's dense. Concrete works because you can make it thick. Water works somewhat if you have enough of it. But here's what's important to understand. Even gamma rays can be managed. Even gamma rays follow predictable rules. Their intensity diminishes with the square of the distance. Meaning, if you double your distance from a gamma source, the intensity drops to 1/4, triple the distance, and it drops to 1/9. Distance and shielding. These are the fundamental tools for protection, and they work because radiation follows physical laws. It doesn't chase you. It doesn't seek you out. It simply radiates, spreading according to geometry and being absorbed according to the properties of matter. Now, let's talk about something that might seem scary, but is actually quite comforting when you understand it. Let's talk about the fact that you, yourself, are radioactive. Yes, you, the person lying there, listening to these words, trying to fall asleep. You are, right now, emitting radiation, gentle radiation, harmless radiation, but radiation nonetheless. Here's why. Your body contains potassium. It's an essential element, necessary for nerve function, muscle contraction, and countless other biological processes. About 0.017% of all natural potassium is an isotope called potassium-40, which is radioactive. Potassium-40 has a half-life of 1.25 billion years. That means if you started with a certain amount of potassium-40, half of it would decay in 1.25 billion years. It's incredibly slow decay, incredibly gentle, but it happens. An average human body contains about 140 grams of potassium. That means you contain about 17 milligrams of potassium-40. And this tiny amount undergoes about 4,400 radioactive decays every single second in your body. 4,400 times per second. An atom of potassium-40 in your body transforms into either calcium-40 or argon-40, releasing a beta particle or a gamma ray in the process. And you're fine. You've always been fine. These decays have been happening since before you were born, and they'll continue until long after you're gone. They're part of the background, part of the natural state of being alive on this planet. You also contain carbon-14, a radioactive form of carbon created in the atmosphere when cosmic rays strike nitrogen atoms. Every living thing absorbs carbon-14 through food and air. An average human experiences about 3,700 carbon-14 decays per second. You contain tiny amounts of uranium and thorium from food and water. You contain radioactive hydrogen, called tritium, in vanishingly small amounts. All of these contribute to your personal radioactivity. If you were to lie down next to someone with a very sensitive radiation detector, they could measure your radioactivity. They could count the particles and photons emerging from your body. And the total? About 8,000 decays per second. 8,000 transformations of unstable atoms into stable ones. And yet, you're fine. You're healthy. This radiation isn't hurting you. It's simply a background hum of atomic transformation, so mild and so distributed throughout your body that it has no meaningful effect on your health. Let me tell you why this is comforting. It means that radiation at low levels is not automatically harmful. It means our bodies have evolved in a naturally radioactive environment and have mechanisms to repair the minor damage that natural radiation causes. It means that the presence of radiation, by itself, doesn't define danger. What matters is dose, energy, and time. What matters is how much, what kind, and for how long. Think of it like warmth. A gentle fire in a fireplace provides comfort. The same fire, if you were to put your hand directly into it, would cause harm, but the existence of fire isn't the problem. The dose, the proximity, the exposure time, these are what matter. Radiation works the same way. The sunlight that warms your face is radiation. The X-ray that helps a doctor see a broken bone is radiation. The radiation from a smoke detector keeping you safe while you sleep is radiation. All different doses, all different purposes, all manageable and understood. Let's drift now to a different aspect of radiation's story. Let's talk about where radiation comes from in the universe, because understanding its origins helps us see it not as an aberration, but as a fundamental part of nature's design. In the beginning, there was light. This isn't poetic language, it's cosmology. About 13.8 billion years ago, the universe began in what we call the Big Bang. In the first fractions of a second, the universe was unimaginably hot and dense. Matter and energy were interchangeable. Particles appeared and disappeared, and the whole universe was flooded with intense radiation. As the universe expanded and cooled, that radiation cooled with it. Today, that primordial radiation still fills the universe. We call it the cosmic microwave background, and you can actually detect it. If you tune an old television to a channel with no signal, about 1% of the static on the screen comes from this ancient radiation, the afterglow of creation itself, still washing over us 13.8 billion years later. This radiation is incredibly weak now, cooled to just a few degrees above absolute zero, but it's everywhere. Every cubic centimeter of space contains thousands of photons from the Big Bang, traveling endlessly, carrying the story of our universe's birth. Then came the stars. When the universe was about 100 million years old, the first stars ignited. These were massive, brilliant, and short-lived. In their cores, under pressures and temperatures we can barely imagine, hydrogen fused into helium, helium fused into carbon, carbon into oxygen, and on up through the periodic table. Each fusion reaction released energy in the form of radiation. This radiation pushed outward, fighting against gravity, keeping the star from collapsing. It was a balance, a dance between the crushing force of gravity and the expansive force of radiation. When these first stars exhausted their fuel, they exploded in supernovae, blasting their enriched material into space. This material, seeded with elements heavier than hydrogen and helium, would eventually form new stars, planets, and eventually, you. But here's the important part for our story. Many of those heavy elements, created in stellar cores, are radioactive. They were born radioactive. When a massive star explodes and creates uranium, that uranium is radioactive from the moment of its creation. It's not that something went wrong. It's that uranium, with 92 protons crammed into its nucleus, simply cannot be stable in its most common forms. So, radioactive elements aren't pollutants or contaminants. They're stardust. They're the ash of stellar furnaces. They're part of the natural inheritance that came from the death of ancient stars. When our solar system formed 4.6 billion years ago, It formed from a cloud of gas and dust that contained radioactive elements. These elements were incorporated into the planets, including Earth. They've been here from the beginning, slowly decaying, releasing heat that keeps Earth's interior molten, driving plate tectonics, creating the magnetic field that protects us from solar radiation. In a very real sense, radioactive decay keeps our planet alive. The heat from decaying uranium, thorium, and potassium in Earth's mantle and core is what drives convection currents deep underground. These currents move the tectonic plates. Plate tectonics creates mountains, recycles ocean crust, regulates atmospheric carbon dioxide, and makes Earth habitable. Without radioactive decay, Earth's interior would have cooled billions of years ago. The magnetic field would have died. Solar wind would have stripped away the atmosphere. Life, if it had ever emerged, would have been extinguished. So radiation isn't just something we tolerate. It's something that made complex life possible. Let's think about another source of radiation that surrounds us constantly: cosmic rays. Cosmic rays aren't actually rays. They're particles, mostly protons, traveling through space at nearly the speed of light. Some come from the Sun, some come from distant supernovae, some come from the violent hearts of distant galaxies. These particles slam into Earth's atmosphere at tremendous energies. When they collide with atoms high in the atmosphere, they create showers of secondary particles. Some of these particles make it all the way to the ground. They pass through buildings. They pass through mountains. And yes, they pass through you. Right now, as you lie there in the darkness, cosmic rays are passing through your body at a rate of about 10,000 per hour. These particles travel through you as if you weren't even there, barely interacting with your atoms, leaving only the faintest trace of their passage. Most cosmic rays don't interact with your body at all. They pass through the spaces between atoms or through the empty space within atoms, emerging on the other side without having done anything. Occasionally, one will strike a nucleus in one of your cells, creating a tiny burst of ionization. Your cellular repair mechanisms fix the damage, usually within minutes. Life on Earth evolved with cosmic ray background radiation. We're built to handle it. At sea level, cosmic rays contribute about 0.3 millisieverts per year to your radiation dose. If you live in the mountains, it's a bit higher because there's less atmosphere above you to shield the rays. If you live in Denver, Colorado, for instance, cosmic ray exposure is about double what it is at sea level. And yet, people in Denver are fine. They're healthy. Studies have found no increased cancer risk from the higher cosmic ray exposure. The dose is so low, and our bodies are so resilient, that it simply doesn't matter. When you fly in an airplane, you're exposed to even more cosmic rays because you're higher in the atmosphere where there's less shielding. A flight crew member who flies regularly might receive an additional 2 or 3 millisieverts per year from cosmic rays. That's about the same as a chest X-ray or two. It's been studied extensively, and while there's some evidence of very slightly increased cancer risk for crew members, it's a tiny effect, and it's complicated by other factors like irregular schedules disrupting circadian rhythms. The point is that radiation exposure from cosmic rays, even the enhanced exposure at high altitudes, is generally not a significant health concern. It's background. It's natural. It's something we've evolved alongside. Now let's drift closer to home. Let's talk about the radiation in your house, in your neighborhood, in the places you go every day. Your home is built from materials that came from the Earth, and the Earth contains radioactive elements. The bricks in your walls might contain small amounts of uranium and thorium. The concrete in your foundation definitely does. The granite countertops that some people have in their kitchens can be more radioactive than other types of stone, because granite sometimes contains elevated levels of uranium. Does this mean granite countertops are dangerous? No. The radiation levels are low. The exposure is continuous but mild. It's like the difference between standing outside on a sunny day and standing under a heat lamp. The dose matters. Some buildings are more radioactive than others simply because of the materials used in construction. The famous Grand Central Terminal in New York City has walls made of granite that emit enough radiation to set off a detector. If Grand Central Terminal were a nuclear power plant, workers there would need to monitor their exposure. But it's not a power plant. It's a train station, and the millions of people who pass through it every year are fine. Because here's a principle worth understanding. Radiation exposure is cumulative, but it's also healable. Your body has mechanisms to repair DNA damage. These mechanisms work constantly, fixing damage from radiation, from chemical exposure, from errors in DNA replication, from countless sources. At low dose rates, the repair keeps up with the damage. The net effect is essentially zero. It's only when the dose rate becomes high enough that damage accumulates faster than it can be repaired that we see health effects. And the threshold for that is much, much higher than natural background radiation. Let me tell you about a place called Ramsar in northern Iran. It's a beautiful area on the coast of the Caspian Sea, known for its hot springs. The hot springs bring water up from deep underground, and that water is rich in radium. The radium has accumulated in the soil and rocks over thousands of years. People have lived in Ramsar for generations. They farm the land. They drink water from wells. They live in houses built from local materials. And their annual radiation dose from these natural sources can be more than 200 millisieverts per year, which is about 100 times higher than the global average. Studies have been conducted on the people of Ramsar to see if this high natural radiation causes health problems. The results? No clear evidence of increased cancer rates, no obvious health effects. The people of Ramsar are, as far as can be determined, just as healthy as people living anywhere else. This doesn't mean that radiation is harmless at all levels. It means that low-dose rate chronic exposure, even at levels far higher than normal background, may not cause the health effects we would predict from studies of high-dose rate acute exposure. The human body is remarkably resilient. Adaptation is possible. Repair mechanisms work continuously, and context matters in ways we're still trying to fully understand. There's a similar story from Kerala, India, where monazite sand on beaches creates areas of elevated natural radiation. People have lived there for thousands of years with no apparent ill effects. And another from Yangjiang in China, where background radiation is 3 times the global average due to thorium in the soil. These natural experiments tell us something important. They tell us that radiation at low levels, even levels higher than what most people experience, is not necessarily harmful. They tell us that our bodies can cope with radiation exposure when it's part of the natural environment. Now, let's talk about something that might seem counterintuitive. Let's talk about the fact that radiation can be useful, even beneficial, and that we use it every day in ways that make our lives better and safer. When you go to the dentist and they X-ray your teeth, they're using radiation to see through your cheek and gums to the bone and teeth beneath. The X-ray dose is tiny, about 0.005 millisieverts, equivalent to about 12 hours of natural background radiation, but it provides valuable information that helps keep your teeth healthy. When you get a chest X-ray, you're receiving about 0.1 millisieverts, roughly equivalent to 10 days of natural background radiation. In exchange, doctors can see your lungs, your heart, your ribs, and diagnose conditions that might otherwise be invisible. More advanced imaging, like CT scans, delivers higher doses, maybe 1 to 10 millisieverts depending on the type of scan. That's equivalent to a few months to a few years of background radiation, delivered all at once. But CT scans can detect internal bleeding, diagnose cancer, guide surgical procedures, and save lives. The key is that these medical uses of radiation are deliberate, controlled, and justified. The benefit of the diagnostic information outweighs the tiny risk from the radiation exposure. Doctors follow the ALARA principle, as low as reasonably achievable. They use the minimum dose necessary to get a useful image. In the early days of X-ray technology, people didn't understand the risks as well. X-ray machines were used casually, sometimes in shoe stores to check how shoes fit. Children's heads were X-rayed frequently to treat ringworm. Radiologists would hold patients during X-ray procedures without any shielding. We learned from those mistakes. We studied the effects. We established safety standards. And now medical radiation is one of the most carefully regulated uses of radiation that exists. Every X-ray machine is tested and certified. Every procedure is justified and documented. Radiation workers wear dosimeters to monitor their exposure. Pregnant women are asked about pregnancy status before X-rays because developing fetuses are more sensitive to radiation. All of these precautions exist because we understand radiation. We know its risks. We know how to minimize those risks. And we know that when used properly, medical radiation does far more good than harm. Beyond medicine, radiation has countless other beneficial uses. Smoke detectors in homes use a tiny amount of americium-241, a radioactive element that emits alpha particles. These alpha particles ionize air in a small chamber. When smoke enters the chamber, it disrupts the ionization, triggering the alarm. The amount of americium in a smoke detector is minuscule, about 0.3 micrograms. The alpha particles can't penetrate the plastic case. Even if you dismantled a smoke detector and held the americium source directly against your skin for hours, the dose would be negligible. But that tiny amount of radioactive material, sitting quietly in a device on your ceiling, could save your life by alerting you to a fire. Millions of homes have smoke detectors. They've prevented countless deaths, and the radiation risk? Effectively zero. In food safety, radiation is used to sterilize or pasteurize certain foods. High-energy gamma rays or electron beams can kill bacteria, parasites, and insects in food without making the food radioactive. Spices are commonly irradiated to reduce microbial contamination. Some fruits are irradiated to extend shelf life. Ground beef is sometimes irradiated to kill harmful bacteria like E. coli. The process doesn't make the food radioactive any more than shining a flashlight on something makes it start glowing. The radiation passes through, does its job of disrupting microbial DNA, and leaves nothing behind. Food irradiation has been extensively studied and deemed safe by health organizations worldwide. It's a tool, like pasteurization or refrigeration, for making food safer to eat. In industry, radiation is used in countless ways. Welding seams in pipelines are X-rayed to check for defects. Radioactive isotopes are used as tracers to track the flow of materials through complex systems. Thickness gauges using radiation help ensure that sheet metal or paper is the right thickness during manufacturing. Radiation has even been used to create better materials. Cross-linking polymers with radiation can make plastics stronger and more heat-resistant. Irradiating gemstones can enhance their color, creating the deep blue of London blue topaz. These uses exist because radiation is a tool. It's a form of energy that can be directed, controlled, and applied to solve problems. And when it's used responsibly, with proper safety measures, it's no more dangerous than electricity or heat or any other form of energy we harness. Let's shift our attention now to something that might bring up more anxiety: nuclear power. Because nuclear power is perhaps the most controversial application of radiation, and yet, when you examine it closely, it's also one of the most fascinating examples of how humans have learned to harness the atom. At the heart of a nuclear reactor is a simple and elegant process. Uranium atoms, specifically uranium-235, are encouraged to split apart. When a uranium-235 nucleus absorbs a neutron, it becomes unstable and splits into two smaller nuclei, releasing energy and more neutrons. Those neutrons can then strike other uranium atoms, causing them to split, releasing more energy and more neutrons. If conditions are right, this becomes a sustained chain reaction, with each fission event triggering others. The energy released in nuclear fission is tremendous. A single uranium atom splitting releases about 200 million electron volts of energy. That doesn't sound like much until you realize that fissioning 1 kilogram of uranium-235 releases about as much energy as burning 3 million kilograms of coal. In a nuclear reactor, this energy is released in a controlled way. The chain reaction is carefully managed using control rods, which absorb neutrons and slow the reaction down. Water, or another coolant, circulates through the reactor, absorbing the heat. That heat is used to make steam, which drives turbines, which generate electricity. It's surprisingly similar to a coal plant, really. Both make heat, both use that heat to make steam, both use steam to turn turbines. The only difference is the source of the heat. In a coal plant, it's chemical combustion. In a nuclear plant, it's atomic fission. But there's a key difference in the byproducts. Burning coal releases carbon dioxide, sulfur dioxide, nitrogen oxides, mercury, and other pollutants into the atmosphere. These emissions contribute to climate change, acid rain, and air quality problems that kill tens of thousands of people annually in the United States alone. Nuclear fission produces radioactive waste, which must be carefully managed and stored. But it doesn't release anything into the atmosphere during normal operation. No carbon dioxide, no sulfur, no mercury, no particulates. The waste is solid, it's contained, and it can be isolated from the environment. Now, I know what you might be thinking. Nuclear waste. That sounds scary. That sounds like it would glow green and mutate anyone who gets near it. But the reality is much less dramatic and much more manageable than popular culture would have you believe. Nuclear waste comes in different forms. The vast majority of it, about 90% by volume, is low-level waste. This includes things like protective clothing, tools, and equipment that have been contaminated with small amounts of radioactive material. The radioactivity is low enough that this waste can be safely buried in shallow repositories after a few decades of storage to let short-lived isotopes decay. Intermediate-level waste includes things like reactor components and chemical sludges from reprocessing. This waste requires shielding and more careful handling, but it's still manageable with current technology. The most challenging waste is high-level waste, which includes spent nuclear fuel. When uranium undergoes fission in a reactor, it creates a complex mix of radioactive isotopes. Some of these decay quickly, within days or years. Others have half-lives of thousands or even millions of years. Spent fuel is highly radioactive and generates significant heat for years after it's removed from the reactor. It must be stored in pools of water for several years to cool down, and then it can be moved to dry cask storage, where it sits in massive steel and concrete containers, passively cooling, safely isolated. The total amount of high-level nuclear waste produced by all the nuclear power plants in the United States over the past 60 years would fit in an area the size of a football field, stacked about 10 yards high. For comparison, coal plants in the U.S. produce about 130 million tons of solid waste every year, much of which contains toxic heavy metals and even trace amounts of radioactive material from naturally occurring uranium and thorium in coal. The challenge with nuclear waste isn't volume, it's longevity. Some isotopes in spent fuel will remain hazardous for thousands of years. This means we need to think about storage on timescales much longer than typical human planning horizons. But here's something comforting. We know how to do this. Geologically stable repositories can isolate waste from the environment for hundreds of thousands of years. Finland is currently building one such repository, called Onkalo, carved into bedrock 500 meters below the surface. The rock formation has been stable for billions of years and will remain stable for millions more. The waste will be placed in copper canisters designed to last for at least 100,000 years. These canisters will be surrounded by bentonite clay, which swells when wet to create an impermeable seal. The tunnels will be backfilled and sealed. The site will be marked to warn future generations. And then, barring human interference, the waste will simply sit there, underground, slowly decaying, isolated from the biosphere. It's not a perfect solution, but it's a workable one, and it's arguably less problematic than releasing carbon dioxide into the atmosphere, where it remains for centuries, or dumping coal ash into ponds where it can leach into groundwater. Nuclear power has had accidents, of course. 3 Mile Island in 1979, Chernobyl in 1986, Fukushima in 2011. These names carry weight. They represent real failures, real releases of radiation, real consequences. But let's look at what actually happened in each case. Because understanding the details helps us understand both the risks and the remarkable safety record of nuclear power overall. 3 Mile Island was a partial meltdown in Pennsylvania. A combination of equipment failure and operator error led to a loss of coolant in the reactor core. About half the core melted. But the containment building, that thick concrete and steel structure surrounding the reactor, did its job. Almost all of the radioactive material was contained. The amount of radiation released to the environment was minimal, equivalent to about a chest X-ray for people living nearby. No deaths, no injuries, no measurable health effects. The accident led to massive improvements in reactor design, operator training, and safety culture. It was a wake-up call, and the industry responded. Chernobyl was far worse. The reactor design was flawed from the start, lacking a proper containment building. During a poorly planned safety test, operators disabled safety systems and pushed the reactor into an unstable state. The reactor went prompt critical, meaning the chain reaction accelerated exponentially. Within seconds, the fuel exploded, blowing the top off the reactor building and exposing the core to the atmosphere. The initial explosion killed 2 workers. In the following days and weeks, firefighters and plant workers fought to contain the disaster, many receiving fatal doses of radiation. 31 people died in the immediate aftermath from acute radiation sickness. A radioactive plume spread across Europe. Thousands of square kilometers were contaminated. Hundreds of thousands of people were evacuated. The long-term health effects are still debated, but estimates suggest a few thousand additional cancer deaths over the following decades from the radiation exposure. It was a catastrophe, but it was also the result of a uniquely bad reactor design operated under a system that prioritized production over safety. Western reactor designs, with their containment buildings and passive safety features, couldn't fail the same way. Fukushima was caused by a natural disaster. A magnitude 9.0 earthquake struck off the coast of Japan, triggering a massive tsunami. The reactors at Fukushima shut down automatically when the earthquake hit, but they needed continuous cooling to remove decay heat from the fuel. The tsunami, arriving about an hour after the earthquake, flooded the site and disabled the emergency diesel generators that were supposed to provide backup power for cooling. Without power, the cooling systems failed. The cores of 3 reactors melted. hydrogen gas built up and exploded, damaging the reactor buildings. Radiation was released into the environment. About 160,000 people were evacuated. The cleanup will take decades. But here's a striking fact. Despite the scale of the disaster, no deaths have been directly attributed to radiation exposure from the accident. The most significant health impact was psychological stress from the evacuation itself. This doesn't minimize the severity of the accident. Fukushima was a serious nuclear disaster, but it also demonstrates that even when multiple safety systems fail, even when the worst happens, modern reactor designs are resilient. The consequences, while significant, are manageable. Compare these accidents to the routine deaths from other forms of energy. Coal mining kills thousands worldwide every year in accidents. Air pollution from fossil fuel combustion kills millions annually. Hydroelectric dams have failed catastrophically, like the Banqiao Dam failure in China in 1975, which killed an estimated 171,000 people. Nuclear power, for all its reputation, has one of the best safety records in the energy industry. Per unit of energy generated, it causes fewer deaths than coal, oil, gas, or even hydroelectricity. This isn't to say nuclear power is without risks. It's to say that those risks are manageable, well understood, and small compared to the risks of alternatives. And new reactor designs are even safer. Modern reactors have passive safety systems that work without power or human intervention. If cooling is lost, natural convection and gravity circulate coolant. If pressure builds up, relief valves open automatically. If the worst happens and the core melts, it's contained in a specially designed core catcher. Small modular reactors, which are being developed now, are simpler, with fewer components that can fail. They can be factory-built and transported to sites, reducing construction costs and improving quality control. The future of nuclear power isn't necessarily large, centralized plants. It might be smaller, distributed reactors providing power to towns and cities, complementing renewable energy sources, providing reliable carbon-free electricity. Because that's the context we need to remember. Climate change is real. It's happening, and we need sources of energy that don't release carbon dioxide. Nuclear power is one of the few technologies we have today that can provide large amounts of electricity without carbon emissions. Every kilowatt-hour generated by nuclear power is a kilowatt-hour that doesn't come from burning coal or gas. It's a kilowatt-hour that doesn't contribute to warming the planet. And in a world facing the challenge of climate change, that matters. Now let's talk about something more intimate and perhaps more concerning to you personally. Let's talk about how radiation affects living tissue, because understanding this helps demystify both the risks and the resilience of life. When radiation passes through your body, it can interact with atoms in your cells. High-energy photons or particles can knock electrons free from atoms, creating ions. That's why we call it ionizing radiation. It ionizes atoms. If this ionization happens in water molecules, which make up about 60% of your body, it can create reactive molecules called free radicals. These free radicals can damage other molecules nearby, including DNA. DNA is the instruction manual for your cells. It's written in a code using 4 chemical letters, and the sequence of those letters determines everything about how your cells function. Damage to DNA can disrupt those instructions. But here's the crucial thing. Your cells have extensive repair mechanisms for DNA damage. Enzymes constantly scan your DNA, looking for errors and breaks. When they find damage, they cut out the damaged section and rebuild it using the undamaged strand as a template. This repair process is incredibly efficient. Every single day, every cell in your body experiences thousands of DNA lesions from various sources: natural metabolic processes, background radiation, chemicals in the environment. And every day, your repair systems fix nearly all of them. It's only when damage is so extensive that the repair systems can't keep up, or when errors slip through and get incorporated into the DNA sequence, that problems arise. If a cell accumulates too much damage, one of two things typically happens. Either the cell triggers programmed cell death, essentially committing suicide to protect the organism, or the cell stops dividing permanently, entering a state called senescence. Both of these outcomes are protective. They prevent damaged cells from continuing to replicate and potentially becoming cancerous. But sometimes, rarely, a damaged cell doesn't die and doesn't stop dividing. Instead, it continues to replicate despite carrying mutations. If the mutations affect genes that control cell growth, the cell might start dividing uncontrollably. That's the beginning of cancer. This is why radiation exposure can increase cancer risk. It increases the number of DNA lesions, which increases the chance that some lesions will slip through the repair systems and lead to mutations that eventually cause cancer. But notice the layers of protection. Ionization has to happen in the right molecule. That molecule has to be DNA. The damage has to avoid being repaired. The mutation has to occur in a gene that affects cell growth. The cell has to avoid triggering its own death. And all of this has to happen in a cell that's capable of continued division. It's a long chain of unlikely events, which is why even moderate radiation exposure doesn't guarantee cancer. It slightly increases the probability. The relationship between dose and cancer risk is complex and still not fully understood, especially at low doses. For high doses delivered rapidly, like those received by atomic bomb survivors or radiation accident victims, we have clear data. The risk of cancer increases with dose in a roughly linear relationship. Double the dose, roughly double the risk. But for low doses delivered slowly over time, the picture is murkier. Some studies suggest that low-dose radiation might actually stimulate protective mechanisms in cells, a phenomenon called radiation hormesis. The idea is that small amounts of damage trigger an adaptive response that makes cells better at repair. Other studies find no protective effect. They suggest that even low doses carry some risk, albeit very small risk. The scientific consensus, used for regulatory purposes, is to assume a linear no-threshold model. This means we assume that any amount of radiation carries some risk proportional to the dose, with no threshold below which there's no risk at all. This assumption is conservative. It's designed to be protective, but it might not reflect the true biological reality at very low doses. What we can say with confidence is that at the levels of radiation exposure most people experience in daily life, the risk is vanishingly small. Natural background radiation, medical X-rays, cosmic rays from air travel, all of these contribute doses that are far too low to cause detectable health effects in individuals. Think about it this way. If you receive an extra 1 millisievert of radiation exposure in a year, which is roughly the dose from a couple of chest X-rays or from living at high altitude, your lifetime cancer risk might increase by about 0.005%. That's 5 in 100,000 or 1 in 20,000. To put that in perspective, your lifetime risk of developing cancer from all causes is already about 40%, or 400 out of 1,000. Adding 1 in 20,000 to that is a change so small it's impossible to measure directly. This is why radiation workers, who receive more exposure than the general public, don't show dramatically elevated cancer rates. They're monitored carefully, their doses are kept below regulatory limits, and the small increased risk they face is accepted as part of their occupation, just as construction workers accept some risk of falls or drivers accept some risk of accidents. Let's drift now to a different aspect of radiation's interaction with life. Let's talk about adaptation, evolution, and the surprising ways that life has learned to cope with and even exploit radiation. Some organisms are remarkably resistant to radiation. The bacterium, Deinococcus radiodurans, can survive radiation doses thousands of times higher than would kill a human. It's been called Conan the bacterium for its toughness. How does it survive? It has multiple copies of its genome, allowing it to reconstruct its DNA from fragments after massive damage. It has highly efficient DNA repair enzymes, and it has cellular mechanisms that protect proteins from radiation damage. This organism wasn't engineered in a lab. It evolved naturally, probably in environments with naturally high radiation or other sources of DNA damage, like extreme dryness. Its radiation resistance is a byproduct of adaptations to harsh conditions. Fungi have been found growing on the walls of the destroyed reactor at Chernobyl. These fungi contain melanin, the same pigment that darkens human skin. Melanin appears to help protect the fungi from radiation, possibly by absorbing energy or by scavenging free radicals. Some researchers have even suggested that these fungi might be able to harness radiation for energy, though this claim is controversial and not yet proven. The point is that life is resilient. Life adapts. Life finds ways to survive in conditions we might think impossible. Even in humans, there's evidence of adaptation to radiation. People living in areas of high natural background radiation, like Ramsar or Kerala, don't just survive. Their cells show enhanced DNA repair capacity. It's as if exposure to slightly elevated radiation has selected for better repair mechanisms or has triggered adaptive responses that make their cells more resilient. This doesn't mean radiation is good for you. It means that life, including human life, has remarkable capacity to cope with environmental challenges. Let's think about radiation from an even broader perspective. Let's think about its role in evolution itself. Cosmic rays and natural radioactivity cause random mutations in DNA. Most mutations are harmful or neutral, but occasionally, a mutation is beneficial. It gives an organism some advantage, some edge in survival or reproduction. Over millions of generations, beneficial mutations accumulate. Harmful ones are weeded out by natural selection, and gradually, organisms change. They evolve. Without mutations, evolution couldn't happen. Without some source of random changes to DNA, life would be stuck, unable to adapt to changing environments. Radiation is one source of those mutations. It's been contributing to genetic diversity, driving evolution for billions of years. In a very real sense, you exist because of radiation. The mutations that led to the evolution of complex cells, of multicellular organisms, of vertebrates, of mammals, of primates, of humans. Many of those mutations were caused by natural radiation. Your ancestors survived cosmic rays and radioactive potassium and radon gas seeping from the ground. They survived, they reproduced, and they passed on their genes, including the DNA repair mechanisms that made survival possible. You are the product of billions of years of life, adapting to a naturally radioactive environment. Radiation is part of your heritage. Now, I want to talk about something that might help put radiation risk in an even clearer perspective. Let's talk about the concept of equivalent risk, because comparing radiation to other risks we face daily can be illuminating. Receiving a dose of 1 millisievert of radiation increases your lifetime cancer risk by about 1 in 20,000. As I mentioned before, But what else carries similar risk? Smoking one cigarette increases your cancer risk by about 1 in 20,000. Drinking 2 ounces of alcohol carries roughly similar risk. Being 10 pounds overweight increases your risk of heart disease by a similar amount. Driving 1,500 miles in a car, you have about a 1 in 20,000 chance of a fatal accident. Living in New York City instead of the countryside exposes you to air pollution that carries similar risk. Eating a charcoal grilled steak with its polycyclic aromatic hydrocarbons carries tiny cancer risk. Drinking coffee with its complex mix of chemicals including some known carcinogens carries tiny risk. The point isn't that all these things are equally dangerous. The point is that life is full of tiny risks. Every choice you make, every breath you take, carries some infinitesimal probability of harm. We accept these risks because the alternative is impossible. We can't live in a risk-free world. We can only try to minimize risks that are significant and accept risks that are negligible. Radiation exposure at low levels falls into the category of negligible risk. It's real, but it's tiny, and it's usually outweighed by the benefits of whatever activity is causing the exposure. Getting a dental X-ray to check for cavities? The radiation risk is negligible compared to the benefit of detecting dental problems early. Flying across the country to visit family? The increased cosmic ray exposure is negligible compared to the joy of seeing loved ones. Living in a house with granite countertops? The radiation is negligible, period. There's no comparison needed because the risk is so small, it's essentially unmeasurable. Let's drift now to a more philosophical space. Let's think about why radiation causes such fear, despite its relatively modest actual danger. I think it's partly because radiation is invisible. You can't see it, smell it, taste it, or feel it. This invisibility makes it seem mysterious and uncontrollable. It's also partly historical. The atomic bombings of Hiroshima and Nagasaki, the Cold War fear of nuclear annihilation, images of mushroom clouds and fallout shelters. All of these created a cultural association between radiation and catastrophe. And it's partly because radiation represents human hubris. We split the atom. We harnessed forces that power the stars. And then we saw the consequences. Weapons capable of destroying cities, accidents at power plants, waste that remains hazardous for millennia. It seems like we've meddled with forces we can't control. But here's another perspective. Radiation is natural. It's ancient. It's fundamental to the universe. We didn't create it, we just learned to use it, for better and worse. And our track record, while imperfect, is actually pretty good. We've used radiation to diagnose and treat diseases. We've used it to generate clean electricity. We've used it to understand the structure of matter and the history of the cosmos. Yes, we've also made weapons with it. Yes, we've had accidents, but we've learned from those mistakes. We've developed safety standards. We've created international agreements to prevent proliferation. We've built better reactors and disposal methods. The story of radiation is, in many ways, the story of human learning. We discover something new. We experiment with it. We make mistakes. We learn. We improve. We try to do better. And all the while, the natural radiation that has always surrounded us continues its quiet work, transforming atoms, carrying energy, shaping the universe at scales, both cosmic and quantum. Let me tell you about some of the beautiful ways radiation has helped us understand the world. Radiocarbon dating uses the decay of carbon-14 to determine the age of ancient objects. When an organism is alive, it constantly absorbs carbon-14 from the atmosphere through food and respiration. When it dies, the absorption stops, and the carbon-14 begins to decay with a half-life of 5,730 years. By measuring how much carbon-14 remains in a sample, scientists can calculate how long ago the organism died. This technique has revolutionized archaeology and paleontology, allowing us to date artifacts, fossils, and geological events with remarkable precision. The Dead Sea Scrolls were dated using radiocarbon analysis. The age of the Turin Shroud was determined this way. Ancient civilizations, extinct species, climate changes from tens of thousands of years ago, all revealed through the gentle decay of carbon atoms. Other radioactive isotopes allow us to date much older materials. Uranium decays into lead with a half-life of billions of years, allowing geologists to date rocks and determine the age of Earth itself. That's how we know our planet is about 4.54 billion years old. The oldest rocks ever found on Earth, in northwestern Canada, are about 4.03 billion years old, dated using uranium-lead dating. The oldest minerals, zircon crystals from Australia, are about 4.4 billion years old. These tiny grains of crystal, dated using the decay of radioactive uranium, tell us that Earth had solid crust and probably liquid water within a few 100 million years of its formation. They tell us the story of our planet's early history, written in the decay of atoms. Radiation has also given us medical treatments that save lives. Radiation therapy for cancer uses high-energy radiation to damage the DNA of cancer cells, killing them or preventing them from dividing. It sounds harsh, and in a sense, it is. Radiation therapy is a controlled use of radiation's destructive power. But cancer cells, which divide rapidly, are more vulnerable to radiation damage than most normal cells. And modern techniques can focus radiation beams with incredible precision, targeting tumors while minimizing exposure to surrounding healthy tissue. Intensity-modulated radiation therapy uses computer-controlled beams that can be shaped to match the three-dimensional form of a tumor. The radiation is delivered from multiple angles, with each beam alone being too weak to cause significant damage, but all beams combined delivering a therapeutic dose to the tumor. Proton therapy uses beams of protons instead of photons. Protons deposit most of their energy at a specific depth, determined by their initial energy. This allows even more precise targeting of tumors with less damage to surrounding tissue. These techniques have cured countless cancers. They've extended lives, they've reduced suffering, and they exist because we learned to understand and control radiation. Radioactive isotopes are also used as tracers in medicine. Technetium-99m is a radioactive isotope with a half-life of 6 hours. It's attached to various molecules that accumulate in specific organs or tissues. Patients are injected with tiny amounts of these tracers, and a special camera detects the gamma rays emitted by the technetium, creating images of bones, hearts, kidneys, or other organs. These nuclear medicine scans can detect tumors, blood clots, infections, and organ dysfunction. The radiation dose is small, typically a few millisieverts, and the information gained can be life-saving. After the scan, the technetium decays quickly. Within a day, most of it is gone. Within a week, it's undetectable. The patient returns to their normal background radiation level, carrying no lasting radioactivity. Radiation has also been used in sterilization of medical equipment. Gamma rays from cobalt-60 can penetrate plastic packaging and kill bacteria, viruses, and other pathogens without damaging the equipment inside. Syringes, surgical gloves, bandages, and countless other single-use medical supplies are sterilized this way. This allows for sterile, disposable equipment, which has dramatically reduced infections in medical settings. Before sterilization techniques became widespread, Hospitals were dangerous places where infections spread easily. Now, thanks in part to radiation sterilization, they're much safer. In agriculture, radiation has been used to create new crop varieties through mutation breeding. Seeds are exposed to gamma rays or other radiation sources, causing random mutations. Most mutations are harmful, and the seeds don't grow, but occasionally, a mutation produces a beneficial trait: disease resistance, higher yield, better flavor, improved nutrition. These mutant plants are selected and bred traditionally to create new varieties. More than 3,000 varieties of crops have been developed this way, including rice varieties that feed millions, wheat that's resistant to drought, and barley used in brewing beer. This isn't genetic engineering in the modern sense. No genes are inserted from other organisms. It's simply accelerated mutation, using radiation to speed up the process that would happen naturally over many generations. The food you eat might include products from mutation breeding, and you'd never know it. The technique is accepted worldwide and considered safe because the final product doesn't contain any radiation and is genetically stable. Now let's think about radiation in space. Because beyond Earth's protective atmosphere and magnetic field, radiation becomes a more significant concern. Astronauts on the International Space Station, orbiting about 400 kilometers above Earth, receive about 150 millisieverts of radiation per year. That's about 50 times higher than the average person on Earth's surface. They're exposed to cosmic rays from outside our solar system, solar protons from the sun, and particles trapped in Earth's magnetic field. The space station's hull provides some shielding, but it's not perfect. High-energy particles can penetrate aluminum and create secondary particles when they collide with the hull material. Despite this elevated exposure, astronauts who spend 6 months on the space station don't show obvious health effects. Their cancer risk increases slightly, by perhaps 3% over their lifetime. NASA monitors their exposure carefully and sets career limits to keep lifetime risk below what's considered acceptable. For missions beyond Earth orbit, radiation becomes more challenging. Traveling to Mars, for example, would expose astronauts to deep space radiation for months with no protective magnetic field. The round trip to Mars, including time on the surface, might expose astronauts to about 1 sievert of radiation, depending on solar activity and shielding. That's a significant dose, roughly equivalent to a lifetime of background radiation on Earth compressed into 2 or 3 years. It would increase cancer risk noticeably, perhaps by 10 or 15%. It's not a trivial risk, but it's also not prohibitive. Many astronauts would accept that risk for the chance to explore another planet. And there are ways to reduce the risk: better shielding using water or hydrogen-rich materials, faster propulsion systems to reduce travel time, forecasting solar storms and taking shelter during high radiation events, underground habitats on Mars to reduce surface radiation exposure. Humanity will solve these problems because we want to explore. We want to extend our reach beyond this planet. And radiation, while a challenge, is a manageable one. Let's think now about the Sun, because our star is essentially a giant nuclear reactor, and understanding it helps us appreciate radiation's cosmic role. At the Sun's core, hydrogen nuclei fuse together under tremendous pressure and temperature to form helium. This fusion releases energy in the form of gamma rays. But those gamma rays don't immediately escape. They're absorbed by atoms in the dense solar interior and re-emitted at slightly lower energy. This happens over and over, with photons bouncing randomly through the Sun's interior, gradually losing energy, transforming from gamma rays to X-rays to ultraviolet to visible light. It takes about 100,000 years for energy created in the Sun's core to reach the surface. That photon you see when you look at the Sun started its journey during the Ice Age, when woolly mammoths still roamed Earth. When the light finally reaches the surface, it escapes into space and travels outward at the speed of light. 8 minutes and 20 seconds later, it reaches Earth. Some of it is absorbed by the atmosphere. Some reaches the ground. Some reaches you. That sunlight, that electromagnetic radiation spanning from ultraviolet through visible light to infrared, is what makes life on Earth possible. It provides the energy that plants use for photosynthesis. It warms the air and the oceans, driving weather and climate. It regulates our circadian rhythms and even helps our skin produce vitamin D. Without the sun's radiation, Earth would be a frozen, lifeless rock. The oceans would freeze solid. The atmosphere would condense and fall as snow. Any life that had somehow emerged would quickly perish. So when you feel sunlight on your skin, remember that you're feeling radiation from nuclear fusion. You're feeling energy that was created by the same process that powers hydrogen bombs, but released gently, continuously, at a distance that makes it warming rather than destructive. The sun also emits higher energy radiation, ultraviolet light, X-rays, and even gamma rays. Most of this is absorbed by Earth's atmosphere and magnetic field. The ozone layer absorbs ultraviolet. The ionosphere reflects radio waves. The magnetosphere deflects charged particles. These protective layers exist because Earth is geologically active, with a molten core generating a magnetic field, and because life itself has shaped the atmosphere. Early photosynthetic bacteria produced oxygen, which led to the formation of the ozone layer, which allowed complex life to colonize land. It's a beautiful, interconnected system. Radiation from space is filtered by Earth's natural defenses, allowing just enough through to sustain life, while blocking the most harmful forms. Sometimes the sun burps out extra radiation in the form of solar flares and coronal mass ejections. These events can temporarily increase radiation levels in space and even affect Earth's upper atmosphere, creating auroras as charged particles interact with atmospheric gases. Auroras, those shimmering curtains of green and red light dancing across polar skies, are radiation in action. They're caused by electrons and protons from the sun colliding with oxygen and nitrogen atoms in the upper atmosphere, exciting those atoms and causing them to emit light. People travel thousands of miles to see auroras. They're considered among the most beautiful natural phenomena on Earth, and they're the visible manifestation of space radiation interacting with our atmosphere. Now let's return to Earth and think about radon, because radon is the single largest source of radiation exposure for most people, and yet it's poorly understood. Radon is a noble gas, element 86 on the periodic table. It's produced by the radioactive decay of uranium and radium in rocks and soil. As it's produced, it seeps upward through cracks and pores in the ground, eventually reaching the surface. In open air, radon disperses and becomes diluted to very low concentrations. But if it seeps into a building, it can accumulate, especially in basements and ground floors where ventilation is poor. Radon itself is radioactive, with a half-life of about 4 days. It decays into a series of other radioactive elements, called radon progeny, which are solid particles that can attach to dust or be inhaled directly. When you breathe in radon and its progeny, they decay in your lungs, releasing alpha particles. These alpha particles can't penetrate far, but they don't need to. They're already inside your lungs, in direct contact with lung tissue. Over years or decades of exposure to elevated radon levels, this can increase lung cancer risk. Radon is the second leading cause of lung cancer after smoking, responsible for about 21,000 deaths per year. in the United States. But here's what's important. Radon risk is highly variable. Some homes have very low radon levels, barely above outdoor air. Others have high levels, hundreds of times higher than average. The only way to know your radon level is to test. Test kits are inexpensive and easy to use. You place a detector in your home for a few days or months, send it to a lab, and get back a measurement of the average radon concentration. If the level is high, above 4 picocuries per liter, a standard used in the U.S., you can take steps to reduce it. Sealing cracks in the foundation helps. Improving ventilation helps. Installing a radon mitigation system, which uses a fan to draw radon from beneath the house and vent it outside, can reduce levels by 90% or more. The point is that radon, while a significant source of radiation exposure, is manageable. You can test for it. You can reduce it. You can make informed decisions about whether mitigation is worthwhile based on your specific situation. Many people live in homes with elevated radon and never know it because they never test. They breathe it for decades and might never develop lung cancer because cancer from radon, like cancer from any cause, is probabilistic, not certain. But testing empowers you. It gives you information, and information allows you to make choices that might reduce your risk. Before we move forward, let's pause for a moment to appreciate something truly remarkable. Every single second of every single day, about 7,000 cosmic ray particles pass through your body. These particles have journeyed across the galaxy, some of them traveling for millions of years through the vacuum of space before encountering you. Each one carries a story written in its energy and trajectory. Some come from the sun, accelerated by solar flares. Others come from supernova remnants, the expanding shells of gas and radiation from stars that exploded before humans evolved. Still others come from beyond our galaxy, from active galactic nuclei powered by supermassive black holes, from pulsars spinning hundreds of times per second, from sources we haven't yet identified. And they pass through you as if you were transparent, which, at their energy scales, you essentially are. Your body is mostly empty space at the atomic level, and these high-energy particles slip between atoms, through atoms, barely noticing your existence. Occasionally, maybe once every few minutes, one of these particles will strike a nucleus in one of your cells. The collision creates a brief shower of secondary particles. Energy is deposited, molecules are ionized, and then, within seconds or minutes, your cellular repair mechanisms identify and fix the damage. This has been happening since before you were born. It happened to your parents, your grandparents, your ancestors, stretching back millions of years. Every human who has ever lived experienced this constant bombardment of cosmic radiation. It's part of the baseline condition of being alive on Earth. The fact that life not only survives this but thrives in spite of it speaks to the resilience of biological systems. We are tougher than we often give ourselves credit for. Our cells are constantly monitoring for damage, constantly repairing, constantly maintaining the integrity of our genetic code against numerous challenges, radiation being just one of many. Understanding this can be oddly comforting. You're built to handle radiation. Your biology has been tested by billions of years of exposure. The mechanisms that keep you healthy in the face of natural radiation are the same mechanisms that keep you healthy in the face of countless other challenges. You are, in a very real sense, a product of radiation. The mutations that drove evolution were partly caused by radiation. The selection pressures that shaped your ancestors included the ability to repair radiation damage. You exist because your lineage successfully navigated a radioactive world for eons. This heritage is written in your DNA, in the repair enzymes that patrol your genome, in the cellular checkpoints that detect damage, in the programmed death pathways that sacrifice damaged cells to protect the whole organism. You are descended from survivors, and you carry their adaptations with you. Let's think about radiation in food, because this is something that sometimes causes concern, but is actually quite interesting when you examine it closely. Bananas contain potassium, and, as we discussed earlier, a small fraction of natural potassium is radioactive potassium-40. A typical banana contains about 450 milligrams of potassium, which includes about 0.017% potassium-40. This means a banana emits about 15 radioactive decays per second. Scientists jokingly refer to banana equivalent dose as an informal way to communicate small amounts of radiation exposure. Eating a banana gives you about 0.001 millisieverts of radiation dose. But here's the interesting part. Your body regulates its potassium levels very carefully. When you eat a banana, you absorb the potassium, but you also excrete potassium to maintain balance. The radioactive potassium in the banana doesn't significantly increase your body's total radioactive potassium content. So while it's true that bananas are radioactive, eating them doesn't meaningfully increase your radiation exposure. Your body's radioactive potassium content remains essentially constant. Other foods contain radioactivity too. Brazil nuts can be quite radioactive because the trees that produce them have roots that reach deep into soil, absorbing radium and other radioactive elements. A single Brazil nut might contain 10 times as much radium as a banana contains potassium-40. Does this mean Brazil nuts are dangerous? No, the amount is still tiny. You'd need to eat many pounds of Brazil nuts daily for years to receive enough radiation to pose any health risk. Long before radiation became an issue, you'd face other health problems from overconsumption. The point is that radiation in food is natural and ubiquitous. Everything you eat contains trace amounts of radioactive isotopes. Your body handles this without difficulty because we evolved eating radioactive food. Speaking of evolution, let's think about the role of radiation in creating the elements themselves, because this is one of the most profound and beautiful aspects of radiation's cosmic story. In the beginning, the universe contained only hydrogen and helium, with traces of lithium. All the heavier elements, everything from carbon to uranium, were created in stars through nuclear fusion and other processes. In the cores of stars, hydrogen fuses into helium, helium into carbon and oxygen, and so on up the periodic table. Each fusion releases energy, which is radiated away as light. But fusion can only create elements up to iron. Beyond iron, fusion consumes energy rather than releasing it, so it doesn't happen in normal stellar burning. The elements heavier than iron are created in supernovae and other extreme events. When a massive star explodes, the tremendous energy and neutron flux allow rapid neutron capture, building heavy nuclei that then decay radioactively into stable forms. This means that every atom of gold, silver, platinum, lead, and uranium was created in a stellar explosion billions of years ago. These atoms were blasted into space, mixed with gas and dust, and eventually incorporated into new stars and planets, including Earth. The gold in a wedding ring, the uranium in a nuclear reactor, the lead in a car battery, all were forged in the death throes of ancient stars. And the process that created them involved radioactive decay, as unstable isotopes transformed into stable ones. When you wear jewelry or handle heavy metals, you're touching atoms that have journeyed across the galaxy, carrying a story that spans billions of years. Some of those atoms are still radioactive, still slowly decaying, still releasing the last whispers of energy from their violent births. It's a humbling and beautiful thought. We are made of stardust, and some of that stardust still glows faintly with primordial radioactivity. Let's drift now to think about radiation in medicine from a different angle. Let's consider diagnostic nuclear medicine and how radioactive tracers can reveal the inner workings of the human body. PET scans, which stands for positron emission tomography, use positron-emitting radioactive isotopes to create three-dimensional images of metabolic processes in the body. A common tracer is fluorine-18, attached to a glucose molecule, creating a compound called FDG. When injected into a patient, this radioactive glucose is absorbed by cells just like normal glucose. Cells that are metabolically active, like cancer cells or active brain regions, absorb more of it. The fluorine-18 decays, emitting a positron. When the positron encounters an electron, they annihilate each other, converting their mass into two gamma rays that fly off in opposite directions. The PET scanner detects these gamma rays and uses the timing and direction to determine where the annihilation occurred. By collecting millions of these events, a computer constructs an image showing where the radioactive glucose accumulated. This allows doctors to see tumors, to assess whether cancer has spread, to evaluate how well treatment is working. It allows neuroscientists to see which parts of the brain are active during different tasks. It's a window into the living, functioning body. The radiation dose from a PET scan is about 5 to 7 millisieverts, comparable to a couple of years of background radiation. The fluorine-18 has a half-life of about 110 minutes, so it decays quickly. Within a day, it's essentially gone. The information gained, however, can be invaluable. A PET scan can detect cancer earlier than other imaging methods. It can distinguish between scar tissue and active tumor. It can guide treatment decisions that save lives. Another fascinating medical use of radiation is radioimmunotherapy, where radioactive isotopes are attached to antibodies that target specific cancer cells. The antibodies seek out the cancer cells and bind to them, delivering radiation directly to the tumor while sparing most healthy tissue. This is like a molecular guided missile. The antibody provides the guidance system, finding the cancer cells. The radioactive isotope provides the warhead, delivering cell-killing radiation with precision. It's still an emerging field, but it shows promise for treating certain types of cancer, particularly lymphomas and leukemias, where cancer cells circulate in the blood and are hard to target with conventional radiation therapy. These medical applications exist because we understand radiation at a fundamental level. We know how different isotopes decay. We know how radiation interacts with tissue. We know how to calculate doses and predict effects. We've turned radiation from a mysterious force into a medical tool. Now let's think about radiation in a more artistic context. Because radiation has inspired art, literature, and culture in fascinating ways. The discovery of radium and its eerie glow captured public imagination in the early 20th century. Radium was marketed as a health product, added to toothpaste, cosmetics, and even drinking water in a misguided belief that radioactivity was beneficial. Radium dial painters, mostly young women, painted watch faces with radium-containing paint so the numbers would glow in the dark. They were told the paint was harmless. They were instructed to lick their brushes to maintain a fine point. Many of these women developed radiation-induced illnesses years later. Their story is tragic, but it led to important advances in occupational safety and radiation protection. Their suffering wasn't in vain. It taught us lessons that protect workers today. The aesthetic of radiation, the idea of glowing green substances and mysterious rays, became embedded in popular culture. Science fiction embraced radiation as a source of superpowers and mutations. Movies depicted giant ants and lizards, created by atomic testing. These cultural artifacts, while scientifically inaccurate, reflected deep anxieties about nuclear technology and the atomic age. They also reflected wonder and fear of the invisible forces humans had learned to unleash. In more recent art, radiation has been depicted with greater nuance. Films like Chernobyl showed the human cost of nuclear accidents while respecting the complexity of the science. Artists have created installations using actual radiation detectors, making the invisible visible through sound and light. There's something philosophically profound about radiation. It's real, measurable, and governed by precise physical laws, yet it's completely imperceptible to human senses. It operates at scales far below our direct perception, in the realm of atoms and subatomic particles. This makes radiation a perfect metaphor for all the hidden forces that shape our world. Gravity, magnetism, quantum fields, all operate beneath the threshold of direct perception, yet they fundamentally determine the nature of reality. Understanding radiation, then, is an exercise in expanding our awareness beyond the obvious. It's learning to trust instruments and mathematics to reveal truths that our senses cannot detect. Let's think about radiation protection philosophy, because the way we approach radiation safety reveals interesting things about risk management and society. The fundamental principle of radiation protection is ALARA, as low as reasonably achievable. This means that even if a radiation exposure is below regulatory limits, we should still try to reduce it further if we can do so without excessive cost or difficulty. This is a conservative approach. It assumes that any radiation carries some risk, so minimizing exposure is always preferable. But it also acknowledges that zero exposure is impossible and that we must balance radiation protection against other factors. For example, lead aprons used during X-rays provide shielding but are heavy and uncomfortable. For a quick dental X-ray, wearing a lead apron reduces an already tiny dose to an even tinier one. The benefit is marginal, but the cost, wearing something uncomfortable for a few seconds, is also marginal. So we do it. But for longer procedures, comfort and mobility might matter more. A surgeon doing a complex procedure under X-ray guidance might choose not to wear full lead protection if it would impair their ability to perform the surgery safely. The slightly increased radiation exposure is accepted because the alternative, impaired surgical performance, poses greater risk to the patient. This kind of nuanced risk-benefit analysis is applied constantly in radiation protection. It recognizes that radiation is just one of many risks we face, and that minimizing radiation at the expense of other important goals isn't always the right choice. Another principle is justification. Any practice involving radiation exposure must be justified, meaning the benefits must outweigh the risks. A diagnostic X-ray is justified if it's likely to provide useful information. It's not justified if the same information could be obtained without radiation, or if the information isn't needed. This is why doctors ask about previous imaging before ordering new scans. It's why children receive lower doses than adults, and why pregnant women are asked about pregnancy before X-rays. Each exposure must be justified based on individual circumstances. The third principle is optimization. For any justified exposure, the dose should be optimized to achieve the necessary outcome with the lowest reasonable exposure. This is why modern X-ray machines use digital detectors that require less radiation than film, why CT scanners have dose reduction algorithms, why nuclear medicine uses isotopes with short half-lives when possible. Every technical advance that reduces dose while maintaining or improving image quality represents optimization in action. These principles, ALARA, justification, and optimization, form the foundation of modern radiation protection. They're applied worldwide, protecting billions of people from unnecessary exposure while allowing beneficial uses of radiation to continue. Let's return to the cosmic scale and think about radiation in the broader universe, because radiation is the primary way we learn about objects too distant to visit. When you look at stars, you're seeing their radiation. The light that enters your eye left those stars years, decades, centuries, or millennia ago, depending on distance. Some stars you can see are so distant that their light began its journey before human civilization existed. But visible light is just a tiny sliver of the electromagnetic spectrum. Stars also emit radio waves, infrared, ultraviolet, X-rays, and gamma rays. By observing these different forms of radiation, astronomers can determine a star's temperature, composition, age, and motion. Spectroscopy, the analysis of radiation across different wavelengths, reveals which elements are present in distant objects. Each element absorbs and emits radiation at characteristic wavelengths, creating a unique spectral signature. By analyzing starlight, we can determine that a star billions of light-years away contains hydrogen, helium, carbon, iron, and other elements. We can measure its temperature to within a few degrees. We can determine its velocity toward or away from us through the Doppler shift of its spectral lines. All this from radiation, from photons that have traveled across vast distances carrying information encoded in their wavelengths and intensities. Radiation also allows us to see through dust clouds that would otherwise obscure visible light. Infrared radiation penetrates dust, allowing astronomers to observe star formation regions hidden in gas clouds. Radio waves pass through dust even more easily, letting us map the distribution of hydrogen gas throughout the galaxy and beyond. X-rays reveal high-energy processes, like material falling into black holes or neutron stars. Gamma rays show us the most violent events in the universe. Supernovae, gamma-ray bursts, matter-antimatter annihilation. Each form of radiation provides a different view of the cosmos. Together, they give us a comprehensive picture of the universe's structure and evolution. And all of this relies on the same fundamental phenomenon we've been discussing. Radiation is radiation, whether it's emitted by a light bulb, a radioactive atom, or a distant quasar. The principles are the same. The physics is universal. Let's think about the future of radiation, science, and technology, because new developments continue to expand our understanding and applications. Research into low-dose radiation effects continues, trying to resolve the question of whether very low exposures carry any risk at all, or might even be beneficial through hormetic effects. Large-scale studies of radiation workers, medical patients, and populations in high background radiation areas provide data, but definitive answers remain elusive because the effects, if they exist at all, are so small. New reactor designs promise even greater safety than current plants. Molten salt reactors use liquid fuel that can drain into passively cooled tanks if temperature rises too high. Traveling wave reactors can consume depleted uranium and nuclear waste. Small modular reactors can be mass-produced and sited flexibly. Some designs use thorium instead of uranium as fuel. Thorium is more abundant than uranium and produces less long-lived waste. Thorium reactors can't easily be used to produce weapons materials, reducing proliferation concerns. Fusion power, the same process that powers the sun, remains an elusive goal. Scientists have been working on controlled fusion for decades, trying to contain and heat hydrogen isotopes to the point where they fuse, releasing energy. Recent advances suggest fusion power might finally become practical within coming decades. The ITER project in France is building a massive experimental reactor. Private companies are pursuing smaller, more innovative designs. If fusion succeeds, it could provide abundant clean energy with minimal radioactive waste. The fuel, deuterium and tritium, can be extracted from seawater. The primary waste product is helium, a completely harmless gas. Fusion isn't entirely radiation-free. Neutrons produced in fusion reactions activate materials in the reactor structure, making them radioactive. But the induced radioactivity is much shorter-lived than fission waste, decaying to safe levels in decades rather than millennia. In medicine, new techniques continue to emerge. Flash radiotherapy delivers extremely high radiation doses in fractions of a second. Early research suggests that this ultra-fast delivery might spare healthy tissue more effectively than conventional radiation therapy, while still killing tumor cells. Theranostics combines diagnosis and therapy, using the same molecule labeled with different radioactive isotopes for imaging and treatment. For example, a prostate cancer tracer can be used first with a short-lived isotope for imaging, then with a longer-lived therapeutic isotope to deliver treatment. Proton therapy facilities are becoming more common, offering precise tumor targeting with less collateral damage to surrounding tissues. This is especially valuable for childhood cancers, where minimizing radiation exposure to developing organs is critical. In space exploration, nuclear power provides a solution for missions where solar power isn't practical. Mars rovers have used radioisotope thermoelectric generators, RTGs, which convert heat from plutonium decay directly into electricity. RTGs have powered spacecraft exploring the outer solar system, where sunlight is too weak for solar panels. The Voyager probes, now in interstellar space more than 40 years after launch, still operate on nuclear power. Future missions to Jupiter's moon Europa or Saturn's moon Enceladus, where liquid oceans might harbor life, will likely use nuclear power. The energy density of radioactive decay is unmatched by chemical or solar alternatives for deep space missions. There's even discussion of nuclear thermal rockets, which would use a nuclear reactor to heat hydrogen propellant, providing much greater thrust than chemical rockets. Such engines could reduce travel time to Mars from 9 months to 3 or 4, significantly reducing crew radiation exposure during transit. The point is that our relationship with radiation continues to evolve. We continue to find new applications, develop better safety measures, and deepen our understanding. Now let's think about something that might help you sleep. Let's imagine radiation not as particles and waves, not as physics and medicine, but as a gentle, constant presence, connecting everything in the universe. Right now, photons from the cosmic microwave background are passing through your body. They've been traveling for 13.8 billion years, cooling and redshifting, and now they pass through you as if you weren't even there. Potassium in your bones undergoes occasional decays, releasing beta particles and gamma rays. These events happen randomly, unpredictably, following quantum probabilities rather than deterministic schedules. Cosmic rays created by distant supernovae pass through you, remnants of stellar explosions that occurred before Earth formed. Sunlight from this morning, stored temporarily in your body's chemical bonds, slowly releases as heat, warming you from within. All of this radiation, natural and ubiquitous, creates a subtle energy field that suffuses your body and the space around you. You've never known existence without it. Every ancestor you've ever had lived in this same bath of radiation. It's not dangerous at these levels. It's simply there, background, context, the baseline state of existence in our universe. In a sense, you're always glowing, not visibly, but if someone had perfect detectors, they could see you emitting faint radiation from radioactive potassium and carbon, from thermal infrared as your body heat radiates away. from electromagnetic fields produced by nerve and muscle activity. You're a tiny source of radiation in a universe full of radiation. You're part of the cosmic glow, connected to stars and atoms and everything that exists. There's something deeply peaceful about this perspective. You're not separate from the universe. You're made of it. The same atoms, the same forces, the same fundamental processes that govern galaxies also govern you. When a potassium atom in your body decays, it's following the same quantum rules that operated in the early universe. When sunlight warms your skin, you're feeling energy that began its existence in nuclear fusion in the sun's core. You're participating in processes that have existed since the beginning of time and will continue long after you're gone. Let me tell you about something else that might comfort you. The fact that radiation follows rules, predictable, mathematical rules that we understand. Radioactive decay occurs randomly for individual atoms, but statistically for large numbers of atoms. Half-life is absolute. If you have a sample of iodine-131 with a half-life of 8 days, exactly half of it will decay in 8 days. Wait another 8 days, and half of what remains will decay. Wait another 8 days, and half again. This predictability means we can calculate exactly how radioactive something will be at any point in the future. We can plan storage of nuclear waste, knowing precisely how long we need to isolate it. The inverse square law for radiation intensity is exact. Double the distance, and intensity drops to 1/4. Triple the distance, and it drops to 1/9. We can calculate the radiation level at any distance from any source. Shielding effectiveness depends on material density and thickness in ways that are precisely quantifiable. We can design shielding to reduce radiation by any factor we choose, given enough material. This predictability, this orderliness, is characteristic of all physical laws. Nature operates according to rules, and radiation, for all its mystery to human senses, follows those rules absolutely. There's comfort in knowing that the universe is lawful. It's not chaotic. It's not random. It operates according to principles that we can discover and understand and use to make predictions. Radiation exemplifies this lawfulness. It seems mysterious because it's invisible, but it's actually one of the most precisely understood phenomena in physics. Let's think about personal radiation exposure one more time, but from a perspective of acceptance rather than fear. You will receive about 2 to 3 millisieverts of radiation this year from natural sources. That's fixed. You can't avoid it. Even if you lived in a lead-lined bunker underground, cosmic rays would penetrate and radon would seep in, and your body's own radioactive elements would continue their decays. You might receive additional dose from medical imaging, from air travel, from consumer products. These exposures, if they happen, are choices you make because the benefits outweigh the tiny risks. You can control some exposures, testing your home for radon and mitigating if necessary, asking doctors if imaging is truly needed, using sunscreen to reduce UV exposure from sunlight. But mostly, radiation is just part of the background of existence. It's like gravity or air pressure. It's there, it affects you, and it's so normal, so baseline, that it's essentially meaningless to worry about it. Your body has dealt with radiation since before you were born. Your cells have repair mechanisms honed by billions of years of evolution in a radioactive environment. You're built to handle background radiation. It's part of your design specifications. Worrying about natural background radiation is like worrying about the fact that gravity is pulling on your bones or that air pressure is pushing on your body. These forces are real, they're measurable, but they're so normal that noticing them is pointless. This doesn't mean you should be careless about radiation exposure. It means you should have perspective. Natural and low-level exposure is effectively harmless. Higher exposures should be justified and minimized. and very high exposures should be avoided. It's a spectrum, not a binary. Radiation isn't either safe or dangerous. It's safe at low levels, manageable at moderate levels, and dangerous at high levels. Context and dose determine everything. Now, as we drift toward the end of our journey through the world of radiation, let's consider the philosophical implications of what we've learned. Radiation represents transformation, unstable atoms becoming stable, energy changing form, matter converting to energy. It's the universe's way of seeking equilibrium, of moving from states of higher energy to states of lower energy. This process is universal. Everything in the universe trends toward lower energy states. Water flows downhill. Heat spreads from hot to cold. And radioactive atoms decay, releasing their excess energy until they reach stability. In thermodynamics, this is the second law. Entropy increases. Order gives way to disorder. But within that overall trend, local pockets of order can emerge and persist. Life is one such pocket of order. Living organisms maintain their structure and organization by consuming energy from their environment, with temporary reversals of entropy, sustained by a constant flow of energy. The sun provides that energy, created by nuclear fusion and delivered to Earth as radiation. Plants capture it through photosynthesis. Animals eat plants or other animals, passing the energy along. And eventually, all that captured solar energy is released back to the environment as heat. Radiation is thus fundamental to life. Without the sun's radiation, no energy input. Without energy input, no life. Everything you are, everything you do, ultimately traces back to radiation from nuclear reactions in the sun's core. Your thoughts, your feelings, your experiences, all are patterns of neural activity, powered by chemical energy that came from food, that came from sunlight, that came from fusion radiation. In a very real sense, you are animated by radiation. You are a temporary pattern in the flow of energy that streams from the sun through the biosphere and back into space. This isn't a metaphor. It's literally true. Remove the sun's radiation, and within days, photosynthesis stops. Within weeks, plants die. Within months, herbivores starve. Within years, the oceans freeze, and all complex life perishes. We exist because of radiation. We persist because of radiation. And someday, when the sun expands into a red giant and then collapses into a white dwarf, the radiation that made us possible will cease, and life as we know it will end. But that's billions of years away. For now, the sun shines, radiation flows, energy circulates, and life continues. There's something almost meditative about this understanding. You're part of a vast energy flow. You're a temporary eddy in the stream of photons and particles that fills the universe. You capture a tiny portion of that flow, use it briefly, and release it back. And this is true for everything. Every living thing, every ecosystem, every planet with life. All are sustained by radiation, shaped by radiation, ultimately dependent on the same fundamental process of energy transformation. Radiation connects everything. The same photons that warmed dinosaurs warm you. The same cosmic rays that struck ancient seas strike you today. The same radioactive elements that heated Earth's interior 4 billion years ago still heat it now, though diminished by decay. You're part of an unbroken chain stretching back to the beginning of the universe. The atoms in your body, the energy animating you, the forces governing your existence, all have histories measured in billions of years. And radiation is one of the threads connecting past to present to future. Slowly decaying isotopes mark the passage of time. Steadily arriving cosmic rays link us to distant stars. continuously flowing sunlight sustains the web of life. Let's think about what radiation teaches us about the nature of knowledge itself. For most of human history, radiation was completely unknown. People lived their entire lives surrounded by it, bathed in it, composed of it, and never knew it existed. This wasn't because they were ignorant or foolish. It was because radiation is imperceptible to human senses. No amount of careful observation, using only eyes, ears, nose, tongue, and touch, could reveal its existence. It took the development of photography, the discovery of uranium's effects on photographic plates, the invention of instruments to detect ionization. Only then could we begin to perceive this invisible aspect of reality. And once we could detect it, we could measure it. Once we could measure it, we could study it. Once we could study it, we could understand it. And once we understood it, we could use it. This progression, from imperceptible to detectable, to measurable to understood to applied, is characteristic of scientific progress. We extend our senses with instruments. We quantify the previously qualitative. We discover hidden patterns. We build theories. We test predictions. We develop applications. Radiation exemplifies this process beautifully. It went from completely unknown to thoroughly understood in just a few decades of intense research. From Becquerel's discovery in 1896 to the first atomic reactor in 1942 is only 46 years. In that brief span, humanity went from not knowing radioactivity existed to understanding it well enough to create sustained nuclear chain reactions and build atomic weapons. The speed of this progress is remarkable. It speaks to human ingenuity, curiosity, and determination. But it also speaks to the power of the scientific method. Observe, hypothesize, experiment, revise, repeat. Radiation was mysterious only until we developed tools to study it. Once those tools existed, the mystery dissolved into understanding. What had seemed magical became mechanical. What had been frightening became familiar. This pattern repeats throughout the history of science. Lightning was once attributed to gods. Now we understand it as electrical discharge through ionized air. Diseases were once blamed on miasmas or curses. Now we know about bacteria, viruses, and genetic disorders. Each time we explain something previously mysterious, we expand our knowledge and our control over the natural world. We trade mystery for understanding, fear for management. Radiation has followed this arc. It's no longer mysterious. We understand how it works, where it comes from, what it does, and how to protect against it when necessary. But knowledge brings responsibility. Understanding radiation means we must make choices about how to use it. These choices have consequences, both beneficial and harmful. The same understanding that allows us to cure cancer with radiation therapy also allowed us to create nuclear weapons. The same physics that powers reactors generating clean electricity also powers bombs capable of destroying cities. This dual nature isn't unique to radiation. Most technologies can be used for good or ill. Airplanes transport people and goods, but also deliver bombs. The internet connects people and spreads knowledge, but also enables surveillance and misinformation. The technology itself is neutral. It's the application that carries moral weight, and we, collectively, must decide how to use our knowledge responsibly. With radiation, we've made both wise and foolish choices. We've developed medical applications that save lives and reduce suffering. We've generated electricity with minimal carbon emissions. We've advanced our understanding of the universe through nuclear physics. We've also built weapons of terrible destructive power. We've had accidents at nuclear facilities that released radiation into the environment. We've created waste that will remain hazardous for thousands of years. Learning from both our successes and our failures, we continue to refine our approach. Safety standards improve, reactor designs become more robust, waste management strategies develop. International agreements limit weapons proliferation. It's an ongoing process. This learning to live wisely with radiation will never achieve perfect safety or perfect wisdom, but we can strive for continuous improvement, guided by evidence, ethics, and humility about the limits of our knowledge. Now, let me bring our journey full circle. Let's return to where we began. The simple fact that radiation is natural, ancient, and ubiquitous. You started this journey perhaps thinking of radiation as something artificial, something dangerous, something to fear. I hope you now see it differently. Radiation is starlight. It's the warmth of the sun on your face. It's the invisible glow of potassium in your bones. It's cosmic rays from distant galaxies passing through you like whispers from the cosmos. It's the slow decay of uranium deep in the earth, keeping our planet's interior molten and driving the tectonic processes that make Earth habitable. It's the diagnostic X-ray that reveals a broken bone. It's the PET scan that detects cancer early enough to treat. It's the radiation therapy that cures tumors and saves lives. It's the smoke detector on your ceiling, silently watching for fire. It's the tracers that ensure food is safe to eat. It's the power from nuclear reactors, generating electricity without carbon emissions. Radiation is all these things and more. It's a fundamental aspect of the universe, neither good nor evil, but simply present. What matters is how we engage with it, with understanding, with respect, with appropriate caution, and with recognition of its benefits as well as its risks. As you lie there, drifting towards sleep, I want you to imagine the universe as it truly is. Not a cold, hostile void, but a cosmos humming with energy, photons streaming in every direction, particles dancing through space, atoms transforming, releasing energy, seeking stability. And you, a temporary pattern in this flow of energy, made of atoms forged in stellar cores, animated by chemical reactions powered by ancient sunlight, quietly radioactive, with the same isotopes that have existed since Earth's formation. You're safe. You've always been safe. The radiation around you is natural and benign. Your body knows how to handle it. Your cells repair damage faster than it accumulates. Your DNA, shaped by billions of years of evolution in a radioactive environment, is resilient. There's nothing to fear in the gentle glow of the universe. Nothing to worry about in the background hum of atomic transformation. It's just the way things are. It's the baseline state of existence. And this baseline state is beautiful in its own way. The universe is not static. It's dynamic, constantly changing, energy flowing and transforming, matter and radiation interconverting, according to Einstein's famous equation, E equals mc squared. You're part of this grand transformation. The atoms in your body will eventually return to the environment. Some will be incorporated into other living things. Some will remain in soil or water or air. Some will undergo radioactive decay, continuing their slow journey towards stability. But for now, for this brief moment in cosmic time, those atoms are arranged in the pattern that is you, thinking, feeling, experiencing, alive. And the radiation that surrounds you, natural and constant, is not a threat but a companion. It's been there since the beginning. It will be there at the end. It's simply part of the fabric of reality, no more alarming than gravity or time. So let your breathing slow, let your muscles relax, let your thoughts drift like photons through the void, purposeless and free. The universe is vast, but you're part of it. The forces governing galaxies govern you too, and those forces, radiation included, are not malevolent. They're not out to harm you. They simply are. Existence is gentle when you understand it. The terror of the unknown dissolves when knowledge replaces ignorance. And radiation, once you know it, is simply another aspect of nature, as unthreatening as the phases of the moon or the changing seasons. You can sleep peacefully in a radioactive world because the radioactivity is mild, natural, and something your body has evolved alongside. You don't need to fear it any more than you fear the air you breathe or the water you drink. It's all just matter and energy, following rules, cycling through forms, temporary and eternal at once. Let yourself be part of that cycle. Let yourself float in the gentle sea of radiation that fills the cosmos. Let yourself be what you are, a pattern of atoms, briefly conscious, soon to dissolve, but for now, wonderfully, improbably alive. The glow is everywhere, soft and continuous. Photons from the beginning of time, atoms decaying in their slow, predictable way, energy flowing from the Sunday cosmic rays from distant stars. All of it touching you, passing through you, connecting you to everything that is or was or will be. And in this connection, there's peace. In this understanding, there's calm. In this knowledge, there's release from fear. Because radiation isn't something separate from you. It's part of you. It's in you. It's around you. It's the universe expressing itself, and you are part of that expression. So rest now. Let the gentle radiation of the cosmos cradle you. Let the knowledge that you understand it bring you comfort. Let the fact that billions have lived and died in this same radioactive environment reassure you. You're fine. You've always been fine. The universe is not hostile. It's simply following its nature. And that nature includes radiation as surely as it includes starlight and gravity and the passage of time. Sleep well, knowing that the invisible glow surrounding you is ancient, natural, and benign. Sleep well, understanding that radiation is simply energy in motion, atoms seeking balance, the universe doing what it has always done. The story of radiation is not a story of danger. It's a story of transformation, of energy, of the fundamental processes that make the universe work. And you are part of that story. You always have been. From the moment of your conception, when radiation from potassium and carbon first began occurring in your cells, through every day of your life, bathed in cosmic rays and radon and potassium-40, until someday far in the future, when the atoms that compose you will return to the earth and continue their slow, radioactive dance. It's all one continuous process, birth and life and death and transformation, matter and energy, radiation and stability, the universe in constant motion, forever changing, forever the same. Rest in that knowledge. Float in that understanding. Let it carry you into sleep, gentle as the beta particles from potassium in your bones, quiet as the gamma rays from cosmic backgrounds, warm as the sunlight that powered your lunch and now powers your thoughts. The radiation is there, always has been, always will be, and it's okay. Everything is okay. The universe is exactly as it should be, and you, dear listener, are exactly where you should be, safe, warm, understood by science, cradled by the cosmos, drifting now into peaceful sleep, surrounded by the gentle glow of a radioactive universe that has nurtured life for billions of years and will continue to do so for billions more. Rest now. Let the science comfort you. Let the understanding bring peace. Let the knowledge of radiation's true nature free you from unnecessary fear. You are safe in the soft glow of the cosmos. You always have been. Sweet dreams. And remember, from all of us here at Sleepy Science, the universe is far more gentle and wonderful than you might have been taught to believe. Every phenomenon, when understood, reveals not danger, but beauty, not chaos, but order, not threat, but simply the universe being itself. Radiation is just one example. There are countless others, and we'll explore them together, one peaceful night at a time. For now, though, sleep. Let this knowledge settle into your mind. Let the comfort of understanding wash over you. Let the soft, invisible glow of natural radiation be a lullaby, singing the song of the cosmos, the ancient melody of transformation and energy, and atoms dancing through space and time. Everything is connected. Everything is energy. Everything is radiation, in one form or another, flowing and changing and seeking balance. And you are part of it all, not separate, not threatened, just part of the beautiful, eternal dance. Good night. Sleep well. And may your dreams be filled with the soft light of understanding, the warm glow of knowledge, and the peaceful certainty that you live in a universe governed by laws you can comprehend, surrounded by forces you can measure, part of a cosmic story that is both ancient and ongoing. The radiation surrounds you like a blanket, invisible and gentle, as it always has, as it always will. Rest now. You are safe. You are understood. You are part of the gentle glow. The end.